Welcome to the deep dive. Grab a seat, get comfortable, and maybe clear your mental workspace for a second, because today we have a truly fascinating journey ahead of us.
We really do.
Yeah, we're looking at a stack of research that feels, honestly, like it's pulled straight out of a science fiction novel. But I promise you, it is very real, and it is happening right now. Today, we are exploring a cutting-edge 2026 research paper.
Right, the one from Jinyu La and that incredible international team.
Exactly. It's titled PathMem, Toward Cognition-Aligned Memory Transformation for Pathology MLLMs. And that team spans the University of Science and Technology of China, Nanyang Technological University, and Imperial College London.
It's a heavy-hitting group.
It is. And the mission for our deep dive today, for you listening, is exploring how scientists are teaching artificial intelligence to diagnose complex diseases, specifically cancer. But they aren't just doing this by feeding the AI a mountain of data and hoping for the best. They're literally teaching the AI to mimic the exact cognitive architecture of a human doctor's memory.
It's a profound shift. I mean, for the past few years, the prevailing philosophy in AI has just been brute scale. You know, build a bigger model, feed it more data.
Or GPUs, more parameters.
Exactly.
Yeah.
But we are now moving away from that brute force data crunching. We're moving towards systems that actively emulate human cognitive processes. The implications here for patient care, for diagnostic accuracy, and honestly, just for our sheer trust in these medical systems are massive.
Okay, let's unpack this. Before we get into the nuts and bolts of how this new PathMem system actually works, we need to understand what is currently broken in the field.
Right.
Let's talk about the current state of multimodal large language models, MLLMs, specifically in pathology. If you follow the AI space, you know these are the powerful systems that can look at complex medical images and process text at the same time.
And they're undeniably impressive.
Oh, absolutely. They do incredible things. But this paper points out a glaring fundamental flaw. The authors referred to current state-of-the-art models as parametric black boxes.
Yeah, that black box nature is the absolute crux of the issue here. Current pathology models, they've been trained on hundreds of thousands of whole slide images. Billions of individual image tiles.
Just a staggering amount of visual data.
Staggering. And through sheer repetition, they've learned to recognize visual patterns incredibly well. But when a human pathologist makes a diagnosis, they aren't just engaging in advanced pattern matching.
Right.
They are linking that specific visual evidence on the slide with highly formal, established diagnostic rules, grading criteria, medical taxonomies, and current AI models lack an explicit, interpretable mechanism to do that. They just don't have a way to dynamically integrate structured domain knowledge while they're reasoning.
So if you've been following how these LLMs are built, you know all their knowledge is baked directly into their pre-training weights, the parameters. So to use an analogy, imagine current AI is like a brilliant medical student who just brute force memorized 1 million visual flashcards right before a massive exam.
That's a great way to put it.
Yeah, they could look at an image of a tumor and immediately output an answer because the statistical weights in their brain trigger a pattern they've seen before. But if you ask them why, if you ask them why that answer is correct or what specific clinical grading rule they used, they can't point to a textbook. They struggle to connect the visual evidence with the formal, documented rules of medicine. They are essentially relying on a highly educated intuition.
What's fascinating here is that without structured knowledge integration and interpretable memory control, these models simply cannot consistently incorporate pathology-specific diagnostic standards, not when they are actually reasoning through a complex case.
Because it's just baked into the wiring.
Exactly. It's parametric inference. The knowledge is baked in a way that we, as the human operators, cannot see, verify, or audit. And when a patient's life is on the line, say you are diagnosing a poorly differentiated carcinoma where the visual signals are incredibly noisy, a good guess based on a black box pattern is unacceptable.
Clinicians need absolute verifiable reasoning.
They do.
Which brings us to the core innovation of this 2026 paper. Since the flashcard method isn't safe enough for high-stakes medicine, the researchers decided to look at human psychology. They analyzed how human pathologists actually process information, and they built PathMem around a hierarchical memory process.
You hit the nail on the head. When a human doctor works, they don't hold the entirety of their medical education in their active consciousness at once. That would be impossible. They rely on two distinct cognitive layers, long-term memory and working memory.
Let's define those for the audience in the context of this AI.
Sure. So long-term memory, or LTM, represents accumulated domain knowledge. For a human pathologist, this is the sum total of their medical school education, the World Health Organization classification textbooks, the grading criteria, the latest clinical evidence from peer-reviewed journals.
It is a vast, persistent reservoir of knowledge.
Exactly.
And obviously, if you try to load all of that into a computer's active processor, or a human's active thought process for that matter, the system crashes. It's way too much context.
Precisely. That is where working memory comes in. WM working memory is the specific, highly relevant subset of knowledge that a doctor pulls to the absolute front of their mind when they are analyzing a specific patient's biopsy slide.
So the case activates the knowledge.
Right. The case-specific evidence selectively activates relevant knowledge from that long-term memory reservoir, brings it into the working memory, and allows the doctor to reason through the diagnosis step by step, iteratively refining their hypothesis.
So mapping this onto AI architecture, we all know about the context window limits of large language models. You can't just paste every medical textbook ever written into the prompt every time you want the AI to look at an image.
No, it causes parameter bloat, it's computationally impossible, and the AI loses track of the information anyway.
Right, so PathMem is designed to solve this. If I'm translating this for you listening, imagine you have a massive library. That's the long-term memory. But when you sit down to write an essay, you only pull 3 specific books to keep open on your desk. That desk is your working memory. PathMem maintains a massive external database and intelligently retrieves only the exact pieces of information it needs for the active prompt.
It's a highly elegant solution.
But that leads to an obvious question. How did they actually build this AI's library, this external long-term memory? I assume they didn't just upload a bunch of PDF files of textbooks.
No, and the methodology here is honestly one of the most robust parts of the research. They engineered a highly structured pathology knowledge graph. To build this graph, they performed a massive, deep semantic search over PubMed.
PubMed.
Yeah.
Wow. So they went straight to the definitive database of global biomedical literature.
They did. They set up an automated pipeline that retrieved literature across thousands of pathology queries. Then they used an LLM to extract structured information from those biomedical abstracts. But to your point, they didn't just dump raw paragraphs of text into a database. They structured this extracted knowledge into what are known as triples.
Triples. Okay, looking at my notes here on the architecture, these triples are essentially breaking down dense medical jargon into a core logical sequence.
Yeah.
Subject, relation, and object.
Yes.
So instead of a paragraph, it distills a paper down to something like lung cancer, arrow, has expression, arrow, TRPA1 mRNA upregulated.
Exactly.
And then it chains that to has diagnostics, SLOE, which points to tumor stage and metastasis risk increases, literally building a logical flowchart out of PubMed.
That's the core of it. It chains these triples together into a vast web, so the logic flows dynamically across all these interconnected nodes. It translates narrative medical research into pure, interconnected mathematical logic.
But hold on a second. Medicine is constantly evolving, and frankly, some published papers get retracted or turn out to be flawed. If they are automating this extraction over all of PubMed, aren't they risking the AI learning bad science?
It's a very valid point.
Because if you let junk data into the long-term memory, the whole system is compromised.
That is a critical vulnerability for any knowledge graph, and the researchers anticipated it. They built a strict filtering mechanism. First, they used a deterministic hashing operator to ensure identical text wasn't entered twice, which prevents redundancy. But more importantly, when the extraction model pulled a triple from an abstract, it also had to calculate a confidence score for that information.
Ranging from 0 to 1, right?
Exactly. And the researchers set a hard threshold at 0.8.
So the bouncer at the door is super strict. Any edge in the graph that scored below an 80% confidence level was just thrown out entirely. But let me push back on that a bit. If you set the threshold that high, aren't we risking throwing out cutting-edge experimental research that might only have a 60% confidence score right now but could become the standard of care tomorrow?
It's a constant trade-off, balancing precision with recall. However, in pathology, where you are establishing definitive ground truth diagnoses based on established taxonomy, high precision is paramount. You cannot base a cancer diagnosis on a low-confidence experimental paper.
Right, that makes sense.
Furthermore, they implemented a probabilistic multi-evidence fusion mechanism to strengthen the graph. If the exact same semantic triple appeared across multiple different independent abstracts, the system mathematically combined them. That increased the overall certainty of that edge in the graph. Corroboration actively increases certainty, just like in human scientific consensus.
Okay, so what does this all mean? We now have an AI, equipped with a flawlessly organized, highly vetted, massive web of medical logic stored as its long-term memory. But the AI is sitting there looking at a gigapixel whole slide image of a patient's tissue. These images are massive, billions of pixels.
They are.
How does it actually use the library? How does it decide which specific logical triples to pull from the library to its desk into its working memory?
This is where the engineering gets truly spectacular. The researchers designed a module called the memory transformer. This acts as the cognitive bridge. It explicitly models the dynamic transition from long-term memory to working memory using a dual-mode activation system, static activation and dynamic activation.
Let's define static activation first.
Static activation acts as the baseline textual filter. When the AI receives a text query from the doctor, for example, what is the grading of this carcinoma? The system compares the mathematical embedding of that query against all the entities stored in the long-term memory graph. It ranks the knowledge entries based on basic cosine similarity.
So for those of you who don't live in natural language processing labs, cosine similarity is basically a way for the AI to measure the mathematical distance between two concepts. If the prompt mentions carcinoma, the math directs the AI to pull knowledge nodes that sit in the carcinoma neighborhood of its database.
Exactly.
That makes intuitive sense. But what is dynamic activation?
Dynamic activation is much more sophisticated because it integrates the visual modality. The model doesn't just look at the text. It aligns the textual embeddings with the actual visual features extracted from the gigapixel whole slide image of the biopsy. The system then jointly projects this multimodal information to compute a global relevance score across the entire knowledge graph.
Oh, wow. So if the image shows specific visual pattern, say distinct glandular structures or signs of cellular necrosis, the dynamic activation module recognizes those visual cues in the pixels and actively fetches the relevant textbook knowledge about necrosis and glandular formation, even if the doctor never typed those specific words into the text prompt.
Precisely. It's reading the image, realizing what it's looking at, and retrieving the context seamlessly.
But there has to be a limit, right? If it sees a highly complex, messy tumor, doesn't it run the risk of fetching too many related nodes from the graph? If you pull too much information to the desk, you run into the exact same parameter bloat issue we talked about earlier.
You're touching on a crucial bottleneck in memory design. To solve this, the researchers conducted an ablation and sensitivity study. They specifically tested how many individual pieces of knowledge, how many tokens from the graph the AI should keep in its active working memory for optimal reasoning. They used a top K token selection strategy to find the exact boundary of activated knowledge. So they simulated pulling one piece of knowledge, then two, then three, and measured the output quality.
So what was the magic number?
The magic number was exactly 5. When top K was set to 5, the model achieved its absolute peak performance across all the testing metrics. It provided just enough rich context to ground the reasoning. But here's the fascinating part. If they gave it 10 or 20 tokens, the performance didn't just plateau, it actually degraded.
Really?
Yes. Flooding the working memory with too much peripheral information cluttered the AI's attention mechanism.
That is intensely relatable. If I'm trying to write an outline for this show and I have 50 browser tabs open, my brain just shuts down. The AI is doing the exact same thing. Just give it the top 5 most relevant, highly scored facts based on the visual and textual data and let the processor do its job.
Right. And mechanistically, the memory transformer applies this top K selection, takes those 5 dense knowledge tokens, and prepends them directly to the original sequence in the transformer encoder. Through this mechanism, the external structured memory is dynamically projected into the model's active space without requiring the model to bloat its own parameters to store that data.
Here's where it gets really interesting. Theory, graphs, and architecture are great to talk about, but the true test of any medical AI is how it performs on an actual, messy, real-world patient case. And the researchers provided a stunning case study in the paper that we have to talk about. The case is labeled LUSC/TCGA-21-1083.
Yes, looking at this specific case illustrates the massive capability gap between PathMem and the previous generation of models.
So for you listening, this was a real biopsy slide from a patient. The ground truth diagnosis, as determined by human expert pathologist, was a poorly differentiated non-keratinizing squamous cell carcinoma, grade 3. This is a tough, aggressive cancer. The researchers fed this exact same slide into several top-tier AI models to see what they would output.
They did.
Let's look at how the competition handled it. Detail the failures, because the way they fail is highly revealing.
They tested it against GPT-4o, which, as many know, is currently a state-of-the-art general-purpose multimodal model. They also tested it against QuiltLava, which is a model specialized specifically for pathology. Both of them failed the diagnosis. Wow. GPT-4 looked at the slide and completely hallucinated. It diagnosed an adenoacanthoma and stated it saw a bronchial-alveolar pattern. It literally hallucinated morphological structures that did not exist on the slide.
And what about the specialized one?
QuiltLava also failed. It diagnosed a moderately differentiated adenoglandular carcinoma.
So both of the competing AI models got confused between squamous cell features and glandular features.
Yeah.
Why is that such a common trap for these systems?
When tumors are poorly differentiated, meaning they have mutated so much that they barely resemble the original healthy tissue, they lose their distinct architectural hallmarks. The visual signals become incredibly chaotic. Squamous cell carcinomas and adenocarcinomas can begin to look very similar at the pixel level if you were only relying on visual pattern matching.
I see.
That is exactly why you need an external, logical long-term memory to anchor the reasoning.
Which brings us to PathMem. How did it handle the exact same chaotic, poorly differentiated slide?
PathMem successfully navigated the chaos. It didn't just guess the right answer, it actively reasoned its way there. It correctly diagnosed the poorly differentiated squamous cell carcinoma. But more importantly, the pathology report it generated specifically cited the evidence it used from its working memory to make that call.
It showed its work.
Exactly. It correctly noted a lack of glandular formation and explicitly stated there was no evidence of vascular invasion. It even correctly identified marked nuclear pleomorphism and high mitotic activity.
It's showing its math, which solves the trust issue entirely. It read the visual cues, the poor differentiation, the chaotic nuclear structure. It went into its library, pulled the exact logical triples related to the non-small cell lung cancer spectrum, dynamically reweighted its focus to suppress the irrelevant glandular facts and boost the squamous facts based on the lack of glandular formation, and delivered a perfect textbook diagnosis.
It's incredible to see it in action.
Now, one case study is great for a narrative, but do we have the overall metrics to back up that this wasn't just a lucky guess?
The data is robust and unequivocal. The researchers evaluated PathMem extensively on the massive WSI bench dataset.
And just to clarify for the audience, WSI bench is a massive benchmark dataset used to test these models. It contains over 179,000 visual question answering pairs. It is the gauntlet for computational pathology.
Exactly. And on the complex task of whole slide report generation across that dataset, PathMem achieves state-of-the-art performance. Let's look at a key metric. WSI precision, which measures how accurate and relevant the AI's generated report is compared to a ground truth human expert. PathMem improved WSI precision by an incredible 12.8%.
That's huge.
And it improved overall WSI relevance by 10.1% over previous models.
Those are massive leaps in a field where teams usually celebrate a 1 or 2% optimization.
And the performance held up in open-ended diagnosis tasks as well, beating prior whole slide-based models by 9.7% in precision and 8.9% in recall. But perhaps the most impressive metric was its performance on zero-shot generalization.
Zero-shot generalization.
What?
This is the ultimate test of true AI reasoning, right?
Yeah.
This is when you test the AI on a completely unfamiliar data set that it has never seen during its training phase to ensure it hasn't just memorized the answers to the test.
Precisely. They tested PathMem on an entirely external, unseen data set called CPTAC-NSCLC. It demonstrated exceptional zero-shot capabilities, scoring an average of 0.754 compared to the specialized QuiltLava model score of 0.603.
Because it's not just pattern matching.
Right. Because PathMem relies on an external knowledge graph rather than just its internal training weights, it can adapt its reasoning to entirely novel images without having to be retrained.
It doesn't need to have seen the specific image before because it understands the fundamental rules of the biology.
If we connect this to the bigger picture, the true victory of the PathMem architecture isn't just about a mathematical model being right a higher percentage of the time. It is about a model being fundamentally interpretable. In the medical field, an AI that is 99% accurate but completely opaque is arguably less useful and certainly far more dangerous from a liability perspective than an AI that is 95% accurate but fully transparent.
Absolutely.
With PathMem, when it outputs a complex cancer diagnosis. The attending human doctor can look at the interface and see exactly which textbook facts, which specific logical triples from the PubMed knowledge graph it pulled from its long-term memory to formulate that decision. The human doctor can verify the AI's logic step by step.
This changes the entire dynamic of how doctors will interact with technology. Whether you are a medical professional listening to this while commuting, a tech enthusiast tracking the evolution of AI architectures, or just someone who might, heaven forbid, one day need a biopsy to see if a tissue sample is dangerous. This research matters to you.
It really does.
We are talking about merging the nuanced, step-by-step, hierarchical memory structures that humans have perfected over evolution with the sheer, unblinking scale of artificial intelligence. It means faster diagnoses when time is critical, it means safer medical care, and it means highly explainable, auditable results. We are finally moving away from the terrifying era of AI black boxes and moving toward having a brilliant, digital, fully accountable colleague in the lab.
This raises an important question, though. As we look toward the future of medical science, we have now mathematically proven that an AI system can flawlessly replicate the human cognitive process of moving long-term knowledge into active working memory. But this AI has an infinitely larger database of medical literature, perfectly memorized in its long-term memory than any human physician could ever hope to read in a dozen lifetimes. If a machine can synthesize global medical knowledge and apply it dynamically to a gigapixel image without fatigue, without bias, and with total transparency, will the fundamentally human trait of medical intuition eventually become obsolete? Or will human doctors simply evolve to use a completely different kind of cognitive skill, one that we haven't even categorized yet, to manage these systems?
Oh, that is a profound thought to end on. If the artificial intelligence holds the entire library of human medical knowledge and knows exactly which books to pull to the desk in a fraction of a second, what does the human doctor of the future actually do with their mind? How does their role elevate? That is something for you to chew on as you go about your day. Thank you for joining us on this deep dive into the architecture of the future. Keep questioning the black boxes, keep learning, and we will see you next time.